silicon thin films synthesized by plasma-enhanced chemical vapor deposition technique. In 1997, he joined a Center for Materials for Electronics Technology, that is CMET, as a scientist. In 1999 till 2000, he visited École Polytechnique Palais-sur France as a Bicast fellow, and there he worked on diamond-like carbon films synthesized by plasma. Presently, he is working on the synthesis of nano-sized metal oxides, metal nitrides synthesized by transferred arc thermal plasma technique. Welcome you, sir. I request Dr. Tanay Seth, sir, to deliver his talk.
Yes, sir.
Good evening to all. I'm going to present the synthesis of nanomaterials by plasma techniques. The plan of talk here is first I will give the introduction, and then why we are synthesizing nanomaterials, then synthesis of nanoparticles techniques. I will cover physical techniques, chemical little bit, and then synthesis by thermal plasma techniques. On that I am presently working, then approach and experimental setup, and then characterization of those nanomaterials and powders, and the result of copper, aluminum nitride, and aluminum nanopowders, which we are synthesizing regularly in our lab, and then conclusion. So first introduction, why importance of nanotechnology. Smaller, faster and cheaper aspect have driven the miniaturization technology in the second half of the 20th century. It has not only witnessed the discovery of supercomputers and internet technology, but what was the beginning of an exciting scientific world, nanotechnology. Nanomaterials totally different electrical, mechanical, magnetic and optical properties from those of the same material in molecular or in bulk form. So if you see here, variation of melting point for gold with size of nanoparticles. It's a bulk gold having melting point around 1065 degrees centigrade. If you see as in the graph, if you are going to from 10 nanometer to 1 nanometer, gold melting point is going to reduce from 1000 to 500 degrees centigrade. So that's the thing when you are going from bulk to nanomaterial, nano size. So why synthesis of nanomaterials? Because nanophase materials, grain size of on the order of 10⁻⁹ meter or nanometer exhibit highly exotic properties, and their industrial demand is steadily increasing. Because they have tunable or tailorable chemical, mechanical and physical properties due to the extremely fine grain size, as I shown here, their melting point are going to reduce with the particle size from 1000 to around 500. So same way one can tune the material, and then high surface to volume ratio and surface energy. Because of high to volume ratio, surface having high catalytic activity can be used. Increased ductility in ceramics, high mechanical strength and micro hardness, enhanced self division, and large thermal expansion. Because of these good properties, these nanomaterials are classified in different from 0 dimensions. All dimension X, Y, Z are nanoscale and less than 100 nanometer, like 0D clusters or spheres. 1 dimensional means 2 dimensional X and Y are nanoscale. Other dimensional are and length is not, like in nano fibers, wires, or carbon carbon fibers, etc. 2 dimensional means 2 dimension means 1 dimension P at the nanoscale, other 2 dimensional are not. Like nano means films, plates or networks, and 3 dimension means no dimension at the nanoscale, all dimension are at the macro scale, bundles of nanowires and nanotubes. And these having different forms, non-crystalline diamonds, ultra-fine powders, metallic powders, crystalline powders, sintered ceramics powders, superalloys, fluorescences, carbon nanotubes, multi-wire carbon nanotubes and colliders, having different applications, like in consumer, personal care, sun care, where zinc oxide, titanium oxides are used. In energy fuel cells, now it's very hot topic. Fuel cells, advanced batteries, solar cells, energy storage, everywhere these nanomaterials are used. In medicines, cell analysis, drug delivery, diagnostics, optical flat panel displays, TFTs, novel displays. In chemical catalytic, because having high surface to volume ratio, that property can be used in catalytic, like multi-use thermal sprays, coatings, paints, and miscellaneous like in space, heat emissions, and defense, like smart metals, people are coating with the silver nanoparticles for antibacterial coatings on that, and then electronics. And synthesis of nanomaterials having means either top-down approach or bottom approach. Top-down approach means methods to produce nanoparticles from bulk material include high ball milling, mechanical processing, etching, electro-explosion, sonication, sputtering, and laser ablation. These processes are done at possible vacuum. Bottom approach means method to produce nanoparticles from atom or chemical process based on transformation in solution, solvent processing, chemical vapor deposition, plasma or flame spring synthesis, laser pyrolysis, atomic or molecular condensation. I will more focus on these processes. I will explain these processes in slides. Synthesis of nanoparticle. Background. Yeah, no, it's okay. Synthesis of nanoparticle techniques means mechanical processing, mechanical milling of solid phases, chemical techniques, solution chemistry, control precipitation, electrodeposition, and solvent processes, vapor techniques, physical vapor deposition, evaporation and sputtering, laser ablation, fire explosion techniques, plasma processing. So I will go in brief a few techniques. This mechanical processing, basically mechanical processing is a process which is routinely used in powder metallurgy and mineral processing industry. In this process, mixture of elements or pre-alloyed powders are subject to grinding under protective atmosphere in equipment capable of high energy compression impact forces such as attrition or So here, because of this balls, materials comes here and then forms the nanoparticle. With this technique, one can go up to few hundred nanometers, and then okay, then chemical techniques, solution chemistry, control precipitation, solver processes, size distribution of semiconductor metal and metal oxide nanoparticles can be manipulated by either liquid introduction or heat treatment, electro deposition, and structure material can also be produced by electro deposition. Vapor techniques. Basically, there are different vapor techniques: physical vapor deposition or evaporation, sputtering, laser ablation, wire explosion techniques, then plasma processing. Here, one can synthesize thin films or in nano particles in the form of thin films. Basically, physical vapor deposition, thin films of different metals are deposited on different substrates. This technique is called condensation from the vapor phase. It's one you can inductive with the heating, melting the material and bringing into the vapors, and then that deposited on the vapors of whatever the substrates are kept there. By the sublimation of evaporating of the material corresponding vapor phase, transportation of the material to the substrate from source, formation of thin films and particles by nucleation and growth. The source can be evaporated by using electron beams. In place of thermal, one can use the electron beam and melt the material and then evaporate and then form the nanoparticle and other things. Then next is the sputtering. Here, atomic level sputtering is the process where atoms are ejected from a target or source material that is to be deposited on the substrate, such as silicon wafer, solar panel, or optical devices. As a result of bombardment, here the gas which is used is the argon gas because it's an inert gas, and argon ions are quite heavy. With the bombardment of argon ion on the target, suppose if you want to deposit silver, you can put silver target here. If you want to deposit gold, one can put gold, or oxides like silicon oxide in the you put silicon and then put oxygen also here. Then one can deposit that silicon oxide over here. Okay. So as a result of bombardment of the target by high energy particles, like many other vapor phase technique, there is no melting of the material. Here, melting is not there, but by the bombardment of the argon ions removes from here by the collision of argon ions, and then that loses that material and then that deposits. Material is done in low pressure or on a cold substrate, or you can deposit on a heated substrate also. And there is a laser ablation. Pulse light form when examiner laser is focused on a solid target inside a vacuum chamber to boil off a plume of energetic atoms of the target material. A substrate position on the intercept of the plume will receive a thin film deposit on the target material. Here it is a laser that is focused on the targeted material. It's melted and then plume is formed, and then on substrate one can deposit here. Next is wire exclusion. It's just like wire exclusion is like in a bulb. If it is fuses, then something deposited around that bulb. So like that, if you with the high pulse discharge, one can burn that wire, or you can explode that wire. High pulse discharge system is used to supply high energy power pulse current to a thin metal wire and lead to the wire explosion. Large amount of heat from the Joule heating will be dissipated in the wire or to melt, evaporate, and subsequently ionize it. Plasma formed during the process expand due to the high temperature and high density. This plasma process will be rapidly cooled during expansion when it interacts with the surrounding gas, and nanoparticles are formed through nucleation process. And now I will go more about plasma processing. What is plasma? Basically, plasma often called a fourth state of matter in an ionized gas comprised of molecules, atoms, ions, electrons, and photons. Basically, if you give sufficient energy to gas to ionize that, and ionization, after ionization, gives the molecules, atoms, ions, electrons, and photons. And because of photons, is that light comes. So that's why it's photons are there, and we can divide this plasma into non-nuclear plasma and nuclear plasma. Non-nuclear plasma, also called cold plasma, means it's a low pressure plasma characterized by high electron temperature and low ion and neutral temperatures, more commonly known as glow discharge. Because after by dissociation of the gas, it's giving some light, it's a glow. That's why it's called a glow discharge. And because it's a cold plasma, called cold plasma also because with the by supplying of the energy as a form of electric energy, you are discharging at low temperature, means at room temperature. So it's called a cold plasma. Equilibrium plasma means atmosphere pressure plasma characterized by high enthalpy content and temperatures around 2000 to 20,000 degree Kelvin. So this is the graph showing the electron density, typical range of temperature and electron density of for the thermal and non-equilibrium plasma. This is non-equilibrium plasma, is cold plasma. Here, electron temperatures are high. Because of electron temperature is high, it gives the sufficient energy to the gas to dissociate. Here is the electron density is low, and electron temperature is also low, but electron density is quite high here. So what is non-equilibrium plasma? Means cold plasma. Here, temperature of electron is higher than the heavier species. Lower electron density 10 to the 19 per meter cube. Inelastic collision between the electrons and heavy particles induce the plasma chemistry. Basically, that electrons induces and then create the plasma. Electron energy remains very high. It's a glow discharge, like or plasma enhanced chemical vapor deposition or microwave discharges. That I'll go to the next few slides. So basically, plasma enhanced chemical vapor deposition. Basically, chemical vapor deposition is a chemical reaction by dissociation with the heat and to form the thin films on the substrate. A reaction can take place. So here, that energy is given by the plasma. So plasma enhance in place of temperature is gives the plasma enhance. That's the plasma enhance the chemical vapor deposition. That give the reaction is a chemical vapor deposition process used to deposit thin films from a gas state vapor to a solid state on a substrate. Chemical reactions are involved in this process, which occur after creation of plasma on the reactant gas. Here, this is the basically organ, or you can say silent plasma. So this is, gives this much color by the putting the RF supply of the 13.5 megahertz. That is the industrial frequency given to the to conduct the experiment. If you put some other energy, other frequency, so it can interact with our communication frequency. So that's the industrial frequency is given 13.56 megahertz. So with this, people are using or this plasma enhanced chemical vapor deposition for the deposition of other slides, what application I will show you. And then this is the microwave plasma. In place of 13.56, 2.45 gigahertz is used in the microwave plasma. Microwave plasma, this is basically used for diamond deposition, microcrystalline or nanocrystalline diamonds films. Here, microplasma is used to activate the hydrocarbon feed and dissociate molecular hydrogen. And then microwave plasma oscillates electrons, which in turn produce ions by colliding with gas atoms and molecules. So, what are the applications for glow discharge? Glow discharge and low pressure, those are plasma enhanced, generally conducted at low pressure. Is a use for plasma assisted chemical vapor deposition for silicon layers, deposition of dopants, anti-reflection coating, anti-scratch layers in optical, solar cells, amorphous silicon, or plasma etching. Basically, these type of discharges are used for the synthesis of synthesis for your chips and other things. Where plasma etchings are used. As an ion source for accelerator, as a light source like UV lamps, vacuum UV source, monochromatic source, plasma etching, and thermal plasma that I will go in more details in subsequent slides is used for melting applications, pre-coatings, sterilization of ceramic particles, like welding, synthesis of nanomaterials, which we are doing here, and waste management in hospitals also, metal cuttings applications. So what is thermal plasma? As I showed in the last slide, what is thermal plasma? Having very high temperature. So activity species here, electrons and radicals, and all are in local thermodynamic equilibrium, because in cold plasma, electron having higher temperature and then ions having low temperature. But here all species of electron temperature and temperature are in equilibrium around 8 to 20,000 degree Kelvin. High energy flux in megawatt per centimeter square, high heating rate, 10 to power 7 Kelvin per second, and steep gradient. Because of that steep gradient, we are forming the nanoparticle. If you are heating at the 10,000 and then cool, we are forming that I'll show you. These are the silent features of thermal plasma. Plasma is a powerful medium to promote high rate of chemical reactions. High enthalpy content of thermal plasma provides high temperature to the miles. High temperature process ceramic nanoparticles can be synthesized. Reduced number of processing steps. Excellent control on size and shape of nanoparticles. Low synthesis time is still in minutes as compared to chemical methods. Here you can get in very short time all reactions, and that's an safe environmental friendly technique. Creation of thermal plasma, depending upon the primary source which can be a DC or AC at main frequency, or at RF, they can known as DCR plasma torches, or RF induction plasma, or hybrid plasma, microwave or hybrid. So this is the basic configuration of DC plasma torches. There is a two electrode devices, the cathode and anode is there, which produce the plasma jet. Gases passes through between these two. It consists tungsten rod cathode. This is the cathode, and a water-cooled copper anode. This is anode shaped in a nozzle. A gas is introduced in the DC arc is established between these two electrodes, and the arc is pushed through the nozzle, resulting in a very high temperature, high velocity flames. And the body of torch consists of cooling chambers and the anode. And this is the showing the induction plasma. Induction plasma is a production via induction heating. When AC current is of high voltage, radio frequency travels via a coil. This is a coil. The conductor located in the middle of the coil. Here the gas is there, flowing gas. The gas is heated up to a high temperature and ionized. This plasma thus produced is known as induction plasma or inductive coupled plasma. And again, DC arc thermal plasma is again divided to non-transferred arc plasma process or transferred arc plasma process. In non-transferred arc plasma process, whatever the material want to avoid is passing these anode and cathode between these two non-consumable electrodes. And electrode may, here disadvantage is that electrode may erode or contaminate the whatever the material is going through it. And transferred arc plasma means here whatever the material you want to synthesize works as a anode, and it is a more efficient process. And here we are using argon as the most commonly gas used. It is used for producing the plasma as a heat transfer medium and for forming an inert shield gas layer. It needs a low voltage to sustain the arc column. The low thermal conductivity helps in forming a narrow restricted column and hence forms a photo arc. This is the simple process I am showing. It's basically whatever the material or can be used a solid or precursor you want to synthesize, bring it to the plasma state, and then quench it. As I shown, what are the advantage? This you can steep gradient is there. So you are quenching from 10,000 to the room temperature. So 10 to a 4 degree Kelvin rate is there quenching, and this forms the nanopowder. Supersaturation condition of the vapor species provide a driving force for the particle condensation, which leads to the production of nanoparticles. And this is nanoparticle formation in the induction plasma. Here, whatever the material or precursor you want to synthesize, you flow through that with the carrier gas. In flight particle, it melts here and then comes into the reaction zone, and then you quench it. So in flight particle here melting is there. This is the basically that in animated form showing how nanoparticles are formed. Here jets of energy like either in DC or in RF provided to the material. Vapors are formed, reactive gases. Suppose if you want to make oxide or nitrates, that reactive gases are reacting with that vapor, and then you are quenching it, nanoparticles are formed. These are the basically few particle synthesis like application electronics technology, silver, gold, or iron having magnetic recording media, on nanostructure ceramics, alumina, means low and high alumina, substrate for HMCs, MLCs, and electronic packaging, aluminum nitride for where you have require high density packaging for external excellent thermal management. Here I am showing several instances of application of in a static and industrial sector like ceramic powders. Here is in chemical like catalysts, zirconium oxide, cesium oxide, different particles, nanoparticles. One can use battery electrodes, lithium cobalt, magnesium oxide, photocatalyst, titanium, explosives. In mechanical, solid lubricants, mononitride, and mold, calcium silicate, and then in fillers, magnesium oxide, iron oxide, zirconium. Abrasive means abrasive zirconium, aluminium, cesium. So many different applications are there in different fields. And this is the transfer thermal plasma reactor, which we installed at Cement, and we are synthesizing by using this reactor different nano powders. I will show you those nano powders synthesized, which we have synthesized here. Basically, this is the heart of the system. This is the plasma chamber. Here, this is the transfer gun is there, and then there is a quench come reaction zone is there, and then there is a cyclone collector is there, and then for pumping there is a liquid pump is there, and then there is a control console is there. There is a 3-level security is there. So, and this is because most of the nanoparticles are highly reactive, so we are collecting all in the glove box control atmosphere. I will show you a few pictures in open anyway. So this is the central graphite shield. Torch is coming from top to here, and we are putting the material in the graphite crucible here. This is the material capped in that central graphite shield part, and then we are covering it, and then from here the torch is coming and going inside. And because it's a very high temperature, and then gas consumption is there, so we have installed a gas piping and many old systems. Here is a argon, nitrogen, hydrogen, oxygen, ammonia, different, and then we have a water chiller to cool that system. So basically, these are the graphical representation of different parameters during synthesis. This is the time, and this two Y scales are there. This is showing reactor pressure, arc voltage, torque power. And I told there are two DC power, 15 kilowatt each are there. So these are the this axis showing the current of those two power supplies. So before starting the plasma, initially we are purging the system, and then we are starting the plasma at 14.5 psia, and then we are putting the power, and then systematically we are increasing the power systematically to melt, then homogenize, and then evaporate the material. And then you can see here we are putting around 350 ampere current, and this is the power around 20 kilowatt, and then melting the material and then cooling the system. So, and then after collection the material, we are synthesizing the nano powder by using scanning electron microscope, atomic force microscope, transmission electron microscope, X-ray diffraction, VT. I will not go in details, just we are using these techniques to characterize the nanomaterials. So we are synthesizing different materials. So synthesis of copper nanopowder by using this transferred arc thermal plasma. So why copper nano? This copper nano having conducting inks and paste containing copper nanopowder, which can be used as a substitute for very expensive noble metal used in printed electronics previously. Now people are replacing that gold and silver by using this copper. Acts as an antibiotic, antimicrobial, antifungal agent when added to plastic coatings or textiles. Can be used as an inner electrode material of a multi-layer ceramic tapesters, as a nano probes in medicine and bioanalytical fields. So for this synthesis of copper nano powder, we put the copper pieces 99% pure in graphite crucible, which acts as an anode. The arc was generated using argon as a plasma gas. These are the different operating conditions. Chamber pressure varied from 10 to 14.5 psi, arc current 125 to 425 ampere, power 10 to 50 kilowatt, and plasma gas we used 95%, or we added little hydrogen also, and pitch gas argon as a 50 to 200 liter per minute. These are the copper nanopowders synthesized at different watt. This is a 20 kilowatt. We synthesized the rate of 150 grams per hour, and then 28 kilowatt, 250 grams per hour. One can see here most of the particles in the nano meter range. This is the STEM at 50K, and here see one can see here it is also 50,000, and these are the XRD of those synthesized copper nano powders. This is again optimized copper powders. This is the AFM showing of those copper nano powder. This is the copper nano powder collected. Then we have also synthesized aluminum nanopowders. Why nano aluminum? There is a great demand for ultrafine aluminum powders in metallurgical, chemical, and paint and pigment industries. Most of the projected application of nano aluminum to exploit the vast quantity of energy stored in the nano aluminum. Basically, most of the nanoparticles of metals are highly reactive. So people want to use those particles for the fuels for space and naval vehicles as a propellant for the military are the areas of greater interest for application of nano aluminum. By the using of nano aluminum, is commonly added to explosives and propellant composition to add energy to burning reactions in propellant and to enhance the blast effect to the explosives. So these are the synthesized nano aluminum powder at different powers, 21 kilowatt and 18 kilowatt, and under different pressures. One can see here most of the particles in the nano meter range. And we have studied with the effect of hydrogen dilution also. One can see with the 20% hydrogen dilution, particles are further going down. These are the optimized nano aluminum powder under 14.5 psi pressure, arc current, power. These are the XRD of those optimized nano aluminum powder. Most of the particles are showing phases, and this is the epicenter, and these are the most of the TM of those particles. Here one can see peaking around 40 to 50 nanometer range. Then we have synthesized aluminum nitride powder also. These are aluminum nitride having high thermal conductivity, greater than 200 watt per meter into Kelvin, which is second to beryllium. Because beryllium is little hazardous metal. Now people are replacing this with the aluminum metal where high thermal management is required. And this thermal expansion coefficient 4 to 5 ppm per degree C also matches with the silicon, and good dielectric properties, high strength, high thermal stability. Please mute it, on mute there. Please mute yourself.
Please mute yourself.
Okay. So for the synthesis of aluminum nitride, we have put reacting gas here, nitrogen or ammonia, and then which gas same thing. Rest of the conditions are same. And these are the different reaction conditions for the synthesis of aluminum nitride. Here, power was 25 kilowatt, and then reacting gas ammonia has a 7 liter carbonate. Here also 7 liter carbonate, and then here is 10 liter carbonate. Here we did at different power, and then here different pressure. And these are the synthesized nanopowders under those conditions. One can see is a 1 lakh magnification. Here it is 50,000. Here also 50,000. You can see most of the particles are less than 100 nanometer. And these are the XRDs of those nanopowders. And these are the optimized nanopowders, which are less than 100 nanometer. Under these conditions, argon 90% and 10% hydrogen, then PSI 25 kilowatt. These are, and we have synthesized 200 gram nano aluminum powder, which we supply to the ISRO. And we have synthesized also copper oxides for some catalytic applications. These are the two different copper oxide. Comparison for copper is also there. You can see here it's a copper and then copper oxide. And then we have synthesized aluminum oxides also by putting the reacting gas oxygen. of the particle. One can see here less than 50 nanometer. This is the XRD of those nanopowders. This is the EDX. Here you can see the oxygen and aluminum concentration. This is the collected aluminum oxide powder. And then conclusion, different techniques are there for the synthesis of nanomaterial. Every technique has its own advantage and disadvantages. And transfer thermal plasma technique was used for the synthesis of nanopowders. Different nanopowder was synthesized and optimized. Copper nanopowder less than 100 nanometer with the production it gives that 250 grams per hour was achieved. Process methodology for the development of aluminum nitride nanopowders with the production rate 50 grams per hour was achieved. And these powders have different application in defense, power, and microelectronics. And thank you.
The session is open for question and answer. If you have any question, any doubt, you can ask in chat box or you can unmute yourself. Our next session is on, thank you, sir.
Yeah.
I'll ask Rishikesh to give vote of thanks. Rishikesh.
Thank you so much, sir,
Yes.
for your valuable time and introducing plasma techniques and its application.
Yeah.
And the lecture was highly informative. All the students will be benefited. Thank you, sir.
I don't know if students understood or not because there is a question.
Yes, sir. And our next,
All of MSc.
so students are from rural background and first year, second year, third year,
Okay.
MSc part one,
MSc
part
part
two,
Okay.
and from chemistry, physics and electronics background.
If any question is there, something anytime you can ask. Yeah, email was there. Yes.
Our next session is on 7th of February, which is on overview of CEMET's in-house restriction of hazardous substances testing facility, which will be delivered by Dr. U. Ramnath. He is a scientist at CEMET Hyderabad. So I hope you will join on 7th of February. We'll share you the link. I've already shared, I think. And see you on 7th. Thank you so much. The session is ended.